So did the talk start already? I didn't get it.
Yes, you can begin.
Okay. Sorry about that. So thank you very much. First I would like to say that of course I feel very honored to be speaking at this occasion of the centenary year of Harishchandra, who has been one of the main figures in our domain, and more particularly in harmonic analysis of local groups. And so his work is everywhere for me, and it's a great honor. I'm also very grateful to the organizer to give me this opportunity to speak online. Unfortunately, I wasn't able to make it, and but I'm still very happy to be able to talk about. So what I'm going to talk about is related to some of the later work of Harishchandra, and more particularly, it's related to one of his earlier attempts to prove local integrability of characters over periodic fields. So I am talking more precisely about his book in the lecture notes called Harmonic Analysis on reductive periodic groups. So it's a lecture notes, I guess number 162. And really what I'm going to say today is, so first it's a work in progress, and it's a small improvement on what Harishchandra did in this book, where he basically proved local integrability of characters for supercuspidal representations over local non-Archimedean fields of characteristic 0. And I will explain how we can use the same technique to show something about fields of positive characteristics. Okay, so let me now introduce the notations. So F will be a local non-Archimedean field of any characteristic for the moment. So more precisely, it means that either F will be a finite extension of QP for some prime number P, or F is isomorphic to the field of Lorentz series over a finite field FQ. And so we will fix G underline over F connected and reductive. And I will just denote by G the F points of G underline. And to simplify the discussion, I will assume that the center of G is compact, but it's not strictly necessary, it just makes things easier to write. So it's just for simplicity. And just to clarify, we will be working with the usual category of smooth representations of G, so we do not by rep of G maybe. Sorry. So this is the category of smooth G representations with complex coefficients. And more precisely, we'll be interested in the set of irreducible objects in that category, so the irreducible smooth complex representations of G. Oh. Seems that my screen sharing stopped for some reason. Sorry. Okay. It should be back now. And okay, so this is a subset of irreducible smooth representations, and we'll also, so another piece of notation, we'll consider two loci in G, so namely the subset of regular semi-simple elements that will be denoted by G reg, as well as the further subset of elliptic regular semi-simple elements that I will just denote by GL. Okay. That being said, so I will now start by stating the main result, which has to do with characters of discrete series. So we, for the moment, just consider an irreducible representation of G, and let me recall what's known about the character of such a representation. So the first thing is that this pi is admissible, and therefore it admits a character in the sense of distribution. So distribution character, which is just, so it's a linear form on the space of smooth and compactly supported function on G, where smooth means, as usual in this setting, locally constant. And it sends such a test function phi to the trace of the operator pi phi, where pi phi is given by integrating phi against the representation, and for simplicity I fix a R measure all along. And something that was also proved by Harishchandra in the generality I'm considering is the existence of a function character. So this is due to Harishchandra. So this function character is a priori just a smooth function on the regular semi-simple locus, with the property that it represents the distribution character on this regular locus. So such that the trace of pi of phi is given by integrating this function against phi. But a priori, this is only proved by Harishchandra for fields of positive characteristics when the test function is supported in the regular semi-simple locus. Okay. And the main question I want to address, so let me call this identity star, is whether this holds for all test functions. Okay. And so it's a well-known and celebrated result of Harishchandra. So if the characteristic of f is 0, where this is due to Harishchandra, or if G is a GLN, where this was this result of Harishchandra was extended by Bertrand Lemaire, we know the following, namely, first, this function character is locally integrable on the group, and the identity star holds for all test function, where now the right hand side makes sense by the property that the character is locally integrable. And I will call this property, which depends on the representation pi, Li pi, so Li is for local integrability. Okay, and this is basically the what I want to talk about. So let me state right away the main theorem I want to discuss. So this is restricted to discrete series, as the title indicates. So let pi be a irreducible discrete series. And let me recall that it means, under the assumption that the center is compact, it means that pi embeds in the space of L2 functions on G. Then, so I would like to make this theorem, state this theorem in two steps. So first, we have the local integrability of the character for pi. And secondly, the function character has a property that is sometimes very useful for applications, namely they satisfy elliptic orthogonality relations. So for any other discrete series pi prime, if we integrate over the space of elliptic conjugacy classes, so let me write the formula and then explain more precisely what are the ingredients. So this is the function character of pi times the complex conjugate of the function character of pi prime. Then this is 1 if pi and pi prime are the same discrete series and 0 otherwise. And here, what I denote by gamma L of G is the set of elliptic regular semi-simple conjugacy classes in G. And the measure is a usual one on this set of elliptic conjugacy classes, but let me recall how it's normalized. So this is given by a formula which is reminiscent of Weil integration formula, so namely we sum over a set of elliptic maximal tori up to conjugacy. And then we integrate over T, or maybe the regular locus in T, for a measure which is some R measure times the Weil discriminant. And we also need to divide by the order of the Weil group to make things work. So this is the Weil group of T in G. And so two things now is we still need to define the R measure. So the R measure on the elliptic maximal tori are normalized so that the total mass is 1. This is one thing. And the second thing is that dg is the usual Weil discriminant, but let me recall the definition because it will be a very important player for my talk. So the Weil discriminant is given by the absolute value of regular function on the group. And more precisely, so dg of G, you can define it as the absolute value of the trace of some exterior power of the adjoint action of G. So D minus L. So this is the highest, this is the first non-zero coefficient in the characteristic polynomial of the adjoint action. So where R of G denotes the adjoint action of G on the Lie algebra. D is the dimension of the group, and L is the absolute rank of G. So okay. So this is the main theorem I would like to discuss. And let me make now two remarks, at least. So the first remark is actually, even if this theorem is only stated for discrete series, we get the local integrability for many other representations, more or less for free. Namely, it's well known that if pi is parabolically induced from some other representation sigma, then local integrability of the character for sigma implies local integrability of the character for pi, essentially by a Van Dyck kind of formula. And therefore, combining point 1 of the theorem with this general fact, we get, so from 1 we get local integrability of the character of pi as soon as the image of pi in the Grothendieck group can be written as a linear combination of representations that are parabolically induced from discrete series. So the sigma I here are discrete series on the Levy, and this is an identity in the Grothendieck group of G. So the Grothendieck group of the category of finite length, smooth finite length representations. Okay. So this gives you a local integrability for many more representations, and for example, basically you get all irreducible representations if your group has, if there is no R groups, or if all the R groups are trivial, rather. And this holds for a group like GLN. So in this case we get local integrability, but this was known before by a work of Lemaire, but this is another way to get it. And for other groups, usually the we don't get local integrability for all irreducible representations because there are non-trivial R groups, and so something is missing, and something about elliptic tempered representations that I don't know how to prove. Okay, and the second remark is about some application of this theorem, and more precisely about part 2 of it, so the elliptic orthogonality relations, and this was also the original motivation actually for that. So namely, the orthogonality relations immediately implies that the restriction of the Harish-Chandra character to the elliptic locus is non-zero for a discrete series. And this was used recently in work of Wittegan, Michael Harris, and Will Sawin, combining this with some argument using a simple trace formula going back to Kashdan to show something about the local Langlands correspondence. So I am going to assume that the characteristic of F is positive here. So in this case, we have a first result towards the local Langlands correspondence, which is very general and due to Genestier and Laforgue. And more precisely, Genestier and Laforgue have associated to any irreducible representation semi-simple L parameter, which you can define as a morphism phi pi SS from the Veil group of F to the L group of G, satisfying the usual conditions. And so what's missing here is the monodromy operator. And I have shown that actually you can always extend, and the extension is moreover unique, this semi-simple parameter to a true L parameter, which is moreover tempered. As expected. Okay. Okay, so maybe I can pause just to see if there are any questions at that point. Okay, so if so,
there don't seem to be any questions.
Okay.
So please, yeah, please continue.
Okay, at least I know that you are still online. And let me now pass to the second part of the talk. So how are we going to prove that theorem? We are going to use, as I said at the beginning, an idea that goes back to Harish-Chandra when he first attempted to prove the local integrability of characters. He proved it for supercomputer representations using what came to be known later as a simple local trace formula. And the main ingredient for the proof will be a result about the convergence of such. So, convergence of a simple local trace formula. Okay, so let me recall the setting. We take pi irreducible discrete series, which will be fixed from now on. And so the starting point is to fix a smooth matrix coefficient of pi, F, which is normalized so that its value at 1 is equal to the formal degree, d pi. Okay. And so picking such matrix coefficient is known since a long time, at least since Harish-Chandra, that we can rewrite the distribution character, so give an integral formula for it. So let me write this integral formula and then I will comment. So the trace of pi of phi is given by a double integral over G of something like this. So f of G conjugate of x times phi of x, and first we integrate over x and then over G. So it might look a bit random if you didn't see this formula before, So let me explain where it comes from first, and why we can see that as some very simple local trace formula. Okay. So the right-hand side of that identity, which depends both on f and phi, I will actually consider it more later as a distribution depending on phi, because we fixed f, right? And we'll study the absolute convergence of that. But first, so as I said, let me explain where it comes from. So explanation. So the thing is that this right-hand side is given actually, so the inner integral, more precisely, it's exactly the restriction to the diagonal of a certain kernel that I'll call K. So where K is the kernel of a certain operator. So more precisely, we consider L2 of G, which is the G times G module for left and right translations, and we let act function f by left convolution and the function phi by right convolution, right? So it's an operator here. And this K, it's easy to see, is exactly the restriction to the, it's the K of GG is the, so the inner integral is the restriction of this kernel to the diagonal. And L2 of G, since pi is assumed to be a discrete series, it contains as a subspace the space of matrix coefficients of pi, which you can identify with contragradient of pi tensor pi. And the point is that since we choose f to be a matrix coefficient of pi, actually LF will basically kills everything else, so it acts by 0 on the orthogonal complement of that subspace, right? And therefore this tensor product operator has a well-defined trace, and of course this trace is given by summing the kernel over the diagonal. So this is just a trace of that operator, which, since it's killing everything in the orthogonal of pi contragradient tensor pi, is just a trace of pi check of f times the trace of pi of phi. And by the normalization on the smooth matrix coefficient of pi on f, this is just 1, and we get the formula that I stated. Okay. So this is to explain where this comes from. And one caveat here, and this is actually the whole difficulty, is that although I have written a double integral in the formula, can I show something? Yeah. We have to be careful that this double integral is not absolutely convergent, but it's only convergent in that order. So more precisely, the integral defining this distribution is only conditionally convergent in general. Okay. Okay, so that being said, I will now try to state the main technical result of that talk, which has to do with the convergence of that simple local trace formula, so more precisely IF of phi. And what I mean by that is that actually the main point is to show that this distribution naturally extends to a bigger space of test functions, which are not smooth on the group, but only on the regular locus. And so to state this result precisely, I need to introduce some auxiliary functions, which will help us to measure first how close 2 points in the group are. So we will need to talk about small scales in the group G, and also how far they are, or close to infinity they are. So we also need to measure the large scale on the group G. So let me do an aparté on that. So small and large scales on G. So I start with the small scale. So the small scale is, we will not choose much about the group, except that it's F locally analytic manifold. So more precisely, I will fix a local chart nearby the 1. So U will denote an open neighborhood of 1, and I will choose an open embedding of U in F to the D, sending for simplicity the neutral element to 0 in FD, and I choose it to be, of course, F locally analytic, and so it's a F locally analytic open embedding. Okay, so we choose one, any that you wish, and using that we can now define some balls inside G. So more precisely, we denote by B bar of R the corresponding closed ball. So this is the set of X in U, such that the norm of I of X for any chosen norm on F to the D is smaller or equal to R. And of course, this will be a sensitive notion only when R is very small, because otherwise it's something which will really depend on the choice of I. Okay, and a slight variant of this will denote by B of XR the translate of that ball by an element of the group X. So it's, let's say, a left translation. Okay, and this we will use to measure how close two elements are, and in particular how smooth a function is. Okay, so then we have also some functions related to the large scale properties of G, which are well known from the work of Harishchandra. But let me introduce them from a slightly different perspective, using this, using balls, let's say. So we fix now a ball in G, and by a ball here I just made a compact neighborhood of 1. And I will assume that it generates G. So such a ball exists because G is compactly generated. And so generating G, by this I mean that G is the union of all positive integers of the power of that ball. Power means you take the product of n elements in the ball. So using that ball, we can now define first a radial function, which will now measure how far you are from 1. So sigma, this is usual Harishchandra notation for this function of x, is the minimum, of so it's a minimal positive integer such that x is in B to the n. And so this is for x in G, and then there is also, we also need Harishchandra a special spherical function, but one way to define it using the ball is as the so it's a normalizing factor between functions and half measures. So you take the volume of x multiplied by our standard ball on the left and the right, and then you take the inverse of the square root of that. But this is up to a logarithmic factor, meaning a power of the radial function. It's essentially Harishchandra special spherical function. In other words, the normalized spherical matrix coefficient of the normalized induce of the trivial representation from a minimal parabolic. Okay, so these are all the functions I will need. And one property, basic property of G, which is also due to Harishchandra, is that G is of polynomial growth, which can be stated using those functions by saying that there is some R such that, so basically you would like to integrate over G, so you multiply the R measure by this Harishchandra special spherical function by to the square. So we are kind of normalizing the R measure so that the measures of all these translates of the, x, b times x times b are more or less 1. And some negative power of the log norm is integrable for that normalized measure. So this is smaller than infinity. And this is something we'll need. Okay, so now I state the main technical result, theorem 2. So it's about the convergence of that local trace formula. And so we need to consider, as I said, functions which are only smooth under regular semi-simple locus. So let phi be a function which is only defined under regular semi-simple locus, and I will impose on phi 3 conditions. So first condition is a support condition. So we'll assume that phi is compactly supported in G. So the support of phi, a priori, it's a compact. It's a subset of regular semi-simple locus, but it's relatively. We assume it's relatively compact in G. So concretely, this means that there exists a compact subset omega, such that phi is supported in omega. That's the first condition. The second condition is a smoothness condition. So we'll assume that phi is smooth, but we'll also need to measure how smooth it is. So smooth means locally constant, and how big are the region where it's locally constant when you go close to the singular set. So the correct the condition imposed here is that there exists epsilon and r positive, such that for all x in the support, phi is constant on some ball centered at x, and the radius will vary with x, and we'll ask it to decay at most polynomially in the Veil discriminant. So it's epsilon, which is the multiplicative constant, times r, the Veil discriminant to the r. Okay. And there is the last condition, which is kind of a gross condition. So we'll assume that phi is bounded. So the absolute value of phi is less than some positive constant. Okay, so just to summarize, condition A is a support condition, condition B is a smoothness condition, and condition C is a gross condition. Okay, so conclusion is then that the distribution IF of phi, which was defined by this, sorry, I should go back a bit, is defined by this expression. So this conditionally convergent double integral is absolutely convergent. Is conditionally convergent, sorry. So let me just say converges in the same sense as before. And we can even be more precise. So there is some quantitative statement now. So more precisely, we have to fix omega, compact subset of G, and 2 positive constants as before. So more precisely, we assume that phi satisfies conditions A and B for some fixed omega, epsilon, and r. Okay. Then there exists a C, so the only remaining free parameter is essentially, okay. The only sensible norm you can define on such space is the uniform norm, the L infinity norm. And there exists a C indeed, such that, so I will just talk about the kernel. So the restriction of the kernel to the diagonal is defined by this inner integral. That so IF of phi is given by further integrating this over G. This is bounded by C times the uniform norm of phi times something which is integrable on G, and this something is exactly what appears in the property, this integral here. So xi g of x squared times a sufficiently negative power of the radial function, so which was the same as before, so that the right hand side is integrable. And this should be G here, right? Okay. So maybe I should pause now again to see if there are any questions.
Please continue.
Okay. Okay, so this I will try to explain the proof in a particular case. But for the moment, I would like to explain how to go from this theorem to the local integrability of characters. And this basically comes from the following corollary. So you take a function phi as in the theorem 2, and I claim that you can rewrite this distribution IF of phi as some limit. And the limit will be given by just truncating brutally so that we stay away from the singular locus. So I will multiply our function by the characteristic function of the locus where the Veil discriminant is bigger than some fixed constant. So where this is the characteristic function of this locus in G. Okay, so maybe I will explain just orally the proof of that corollary, because it just follows directly from this identity. Namely, these functions, when t varies, they obviously satisfy A and B for uniform omega, epsilon, and R. It's relatively easy to see. You have to show something about the smoothness of that function, or maybe the smoothness of the Veil discriminant, more precisely, but this is something completely general about absolute values of polynomial functions or regular functions. But once you have this, you can show that, so these functions, they satisfy A and B, so they are for uniform omega, epsilon, and R, so they are as in some fixed Banach space, as in this estimate. And this estimate will give you, will show you that the integral defining IF is, the integrand in the integral defining IF is dominated by an integrable function. And therefore, applying a Lebesgue dominated convergence theorem, you get the result. This is basically all. So let me now explain how the corollary further imply the local integrability of the character of pi, where pi is once again a discrete series that I have fixed. So we will do the proof in two steps, because the local integrability it claims two properties. First, the fact that the function character is locally integrable. This is the first thing we need to show. So we'll fix some compact subset in G. And we need to show that the function character is integrable over omega. So here is a fact whose proof I will not explain during the talk. I will be happy to explain further during the questions. But the fact is that the function character is a smooth function under Galois locus, but we can also measure how smooth it is, and it will indeed be smooth. The smoothness will be of this form. So more precisely, there exists epsilon and R, positive constant, such that for all x in omega, which is also regular semi-simple, theta pi is constant on the ball centered at x with radius epsilon times the Veil discriminant to the R. Okay. So it does not mean that we can apply theorem 2 to the character, because, for example, the character will certainly not be locally bounded in general. But we can apply it to a closely related function. So recall that at the end we would like to take the absolute value of the character. So basically we multiply it by the phase of the character. So in formula this says that you take theta pi of x divided by its absolute value if x is in omega and the Harish-Chandra character is non-zero at that point and zero otherwise. So this is a smooth function on the regular semi-simple locus, and it satisfies, now it's easy to see, A, B, and C. So the crucial condition is B, and this is because of the previous fact about the function character. Okay, and now we can apply the corollary to deduce that the limit when t goes to 0 of if of phi times the characteristic function of the locus where the Well discriminant is bigger than t. This is something, in particular it converges. But now, when we multiply phi by the characteristic function of the locus where the Well discriminant is bigger than some small but positive constant, you get a smooth compactly supported function, so a usual test function. And therefore, by the original motivation for studying this distribution, we know that this is given by integrating the character against the test function and by the choice of test function. So maybe I should put a bar here actually, I realize now. But this doesn't change anything. So complex conjugation, you get the integral over omega intersected with the locus where the Well discriminant is bigger than t of the absolute value of the function character. This is for fixed t, and since it has a limit when t goes to 0, you deduce that the function character is indeed integrable over omega, and since omega was arbitrary, this is showing that theta pi is locally integrable. So this is the first step. And the second step is easier actually, because now you would like to compute the distribution character in terms of the function character. So you start with usual test function. So now phi is just the usual test function. But the usual test function, we can still apply the corollary, right? So we can still write EF of phi, but EF of phi, recall, is just giving you the distribution character as the limit when t goes to 0 of EF. That. And once again, now when t is positive, the test function is supported in the regular semi-simple locus, and therefore we can apply the definition of the function character. This is just the integral over the locus where the Well discriminant is bigger than t of theta pi against phi. And when you take the limit when t goes to 0, since we have already shown that the Alexandra character is locally integrable, this is just the integral over g of theta pi against phi, and it gives you the representability of the distribution character by the Alexandra character. Okay. I still have some, so let me pause again to see if there are any questions so far.
There is one question.
Okay.
Small r that was in theorem 2.
Sorry, excuse me. There is some echo, so I didn't hear the question very well. But
the small r that is in theorem 2.
The small r, yes.
It's arbitrary,
yes.
or it's exactly the one from before.
So this one.
Right.
It's arbitrary, yes, it's arbitrary indeed, but I only stated it for what it suffices to have it for r sufficiently large so that this is satisfied. But that's right, so otherwise, maybe I right click like this, then there is a constant depending on r, and this is true for all r.
Thank you.
Okay?
Yes, please.
Okay. So if there are no other questions, let me, so I still have maybe 15 minutes. So I will try to explain the proof of theorem 2. So theorem 2 is, once again, this about the absolute convergence of the local, simple local trace formula for some non-smooth or non-usual test functions. In a particular case, so actually I will concentrate on the first non-trivial case, which is PGL2. So we'll assume that G is PGL2. And also to simplify, I will assume that pi is supercuspidal. Because then the test function is, the matrix coefficient is also compactly supported, and this will make the discussion easier. Also, we can deal with a general case, but then we have to use some bound on the matrix coefficients, and also at some point we have to use something like our conjecture. Okay, so we'll only use one thing about the test function. About the matrix coefficient. We use that it's very cuspidal in the sense of Asperger, or maybe Arthur also. So very cuspidal, let me recall what it means. It means the following. It means that whenever you integrate f along the unipotent radical of any proper parabolic subgroup, times an element in the Levy component, it is 0. So let me write it here. So any proper parabolic subgroup here is conjugated, it's a Borel subgroup, so it's conjugated to the standard Borel subgroup. So set B to be the standard Borel subgroup of PGL2, so the subgroup of upper triangular matrices, with the usual Levy decomposition AN, so N is the unipotent radical and A the subgroup of diagonal matrices. So for all G in G, and all A in A, I will write it this way. When you integrate of N, F of G inverse A U G, so we integrate over the unipotent radical, but since we have conjugated by G, it's like integrating over the unipotent radical of the G conjugate of B against an element in some Levy component, so here just a maximal torus. This is 0. And just one comment is that matrix coefficients of supercuspidal representations, they satisfy a much stronger condition, which is called supercusp form by Arichandra, meaning that when you integrate over the unipotent radical of any proper parabolic against any element of the group, not necessarily in a Levy component, you get 0. But we'll just use that property, and this property in particular still holds for matrix coefficients of discrete series. Okay, so let's start the proof. So the proof basically, we first restrict. So recall that we want to do is to maybe I should go back just 1 minute. We want to show that estimate whenever phi is a test function as defined in this theorem. So that's satisfying the three conditions: one on the support, one on the smoothness, and one on the growth. So we'll first restrict restrict ourselves to particular G. So namely, we'll use a Cartan decomposition. So let K be the standard maximal compact subgroup of G, and lambda plus will be so it's basically positive Eigenvalue. So it's a subgroup of A consisting of elements of this form, where N is non-negative, and pi is a uniformizer, as usual, and I will denote for simplicity this element by AN. So this is a submonoid of A. And we have the Cartan decomposition. G is equal to K lambda plus K. And from that, it's easy to see that, to deduce that we just need to bound. So when G goes to infinity, it's like the lambda plus part is going to infinity, and we can restrict to the case where G belongs to lambda plus. So we need to bound that, right? In terms of N. Okay. So to do that, the integrand here is given by integrating the f to which we have applied the conjugation action of an times phi. So it's very natural to look at the by conjugation of this monoid on G. And two basic facts about that action. So first we can look at the subset of fixed points. And this is obviously just the standard maximal torus. And the attractor set, so by the attractor I mean the subset G plus of G in G, such that when you do AN, so you conjugate G by AN inverse, it has a limit when n goes to infinity, which automatically will be a fixed point, is equal to the opposite of the standard Borel, so B bar, the subgroup of lower triangular matrices. So in other words, it's telling you that if you are outside of B bar, then conjugation by AN inverse will tend to infinity, right? And you can make this quantitative. This is the following fact. There exists some absolute constant, and you can just choose it sufficiently large, such that if you take so now we won't look at elements we are not in the attractor set, but in some small neighborhood of the attractor set. So a small neighborhood can be obtained by multiplying this by a small ball in N. So this is by definition the subgroup of elements like this, where the absolute value of U is smaller than C times Q to the minus N. Okay, so if G does not belong to this small neighborhood of the attractor set, then either G is already very far, so more precisely G is not in the support of our test function phi, which recall is at least compactly supported on the group, or maybe it's still in the support of phi, but then since it's not very close to an element in the attractor set, then conjugation by AN will send it very far. And AN is not in the support of F. So this is why I use the simplification that pi is supercuspidal, because F is compactly supported. Okay, so that's actually not so hard to show, but at least I hope I motivated this fact somehow by describing the attractor set. And therefore, so this is for n large enough, maybe. We can rewrite the function we are interested in, Kan here. This integral, you can restrict it to this subset. So let me write it. So it's basically an integral of n bar times a times this very small rule in n, right? So when n is large, this is very small, and times some measure. So if you want to be completely precise, you have to multiply by some modular function. Okay, so now let's look at what inside the integral. So the first thing is I would be forced to explain a few things orally, so I hope it's fine. So this phi is compactly supported, and this will impose that the U bar and T variable, they are constrained to be in compact subset if you want this part to be non-zero. Okay. And when n is very large, the conjugation of by AN inverse of U bar will be very small. And so if n is very large, this is by smoothness of F. So if F is uniformly smooth, it's just a matrix coefficient. This is invariant by the AN conjugate of U bar, and this is just F of T times NU AN. And we would like to do the same for phi, because U is in a very small net of 1 in n, and therefore if phi was smooth in the usual sense, this would be invariant by U on the right for n sufficiently large. But our test function is not necessarily smooth uniformly smooth. but at least we have some control on the smoothness. So more precisely, what we get from the smoothness condition on phi is that phi of u bar tu is phi of tu, unless because we know the phi is is constant on some ball centered at tu. Oh no, I write it in the wrong direction, sorry. Centered at u bar t, so it's u, which is very small here, of reduce basically some power of the Veil discriminant. Right, so unless the Veil discriminant of u bar t is very small. This is the same as the Veil discriminant of t. And our small, basically smaller than some q to the minus n divided by some big constant r, which is basically the same exponent that appeared in the statement about the smoothness of phi. So it was the exponent of the Veil discriminant. So this is why we use the smoothness assumption. Okay. So using that, at least when the Veil discriminant of t is not too small, we can rewrite this as okay, so let me do now, there is a small change of variable, of course, because now we'll replace u by an inverse, sorry for the technicality, but so that we really get an integral over n in f. But we get basically, we get that, right? And there is a factor here coming from the change of variable. And phi is invariant on the right by u. This is provided the Veil discriminant is of t is bigger than q to the minus n to the r up to some constant times some measure. So I will not so du bar dt du maybe. So this is somehow the main term, and then there is a reminder. So this is the same integral, except that phi is not invariant by u. And this is when the Veil discriminant of t is very small, times the same measure. Okay, and so now the thing is that the first term, so the first term in the sum is 0, because it contains as an inside integral the integral over n of f of tu du for c. So c was arbitrarily large from the beginning, if you remember, so this is just 0 if we choose c large enough from the beginning. And we just, so the kernel function now is reduced to the error term, which we can now bound. So this is basically smaller than this times. Now we can just bound everything brutally, so f and phi by some constant. So we call that phi. Now we'll use the gross condition. So phi bounded plus the fact that the two functions are compactly supported. So compact. To get, so we can integrate over u in u bar and get at the end something like this. An integral over the torus. But we're integrating, so omega is some compact subset depending on the supports of our functions, right? But basically we're integrating on the compact subset on the locus where the Veil discriminant is very small. So something I didn't say is that this modular character is essentially just the square of Arichandra psi function as before. It's easy to see. And okay. And the fact is that now we have gained something here, because once again, some general properties about functions given by absolute values of polynomial functions. This integral will be bounded by q to the minus delta. We have a delta saving here for some delta very small but positive. And this is in particular smaller than any negative power of the log of the radial function. And so all in all, we get exactly what we want. Oh, and there is maybe, since we want something which is uniform in phi, also we have bounded phi just by a constant, so here we have the uniform norm of phi. And we get exactly what was claimed, I think. Okay, and so that's about it. So I think I already exhausted my time, so let me stop there, and thank you for your attention.
Thank you. Any questions? Yes.
This echo.
The mic is yeah, it's muted.
Can you hear me, Raphael?
Yes, yes, I can hear you, depend on.
Okay. This local integrability is closely related to the fact that the character times the square root of the discriminant is bounded.
That's right.
Your proof you prove this, or
I'm afraid not. So the method is too soft to prove something like this. So basically, the only thing that comes out of the proof is that, at least as far as I can tell, is that if you multiply, the function character by some high power of the Veil discriminant is bounded. But yeah, and I think it's maybe not even true in the case of positive a local field of positive characteristic, that the correct factor to normalize the rational character is the square root of the Veil discriminant, because even for SL2 over local field of characteristic 2, I think you have to include an extra term which comes from the discriminant of the torus, because there are infinitely many elliptic tori, for example, in this case.
all right? Just one more question. You said you proving characteristic positive, but maybe your proof is working for all local fields?
Yes, I'm not using at all the fact that the field is of positive characteristics, although it creates more some technical, some technical problems to deal with positive characteristic fields, but the same proof works for fields of non-Archimedean fields of characteristic 0, but of course it's
not real
much
numbers.
less. Not over real number, no.
This proof doesn't work for real numbers?
No, because I don't know how to formulate something similar to smoothness condition over the real number, for example. But I didn't really think about it actually, but it might be.
So is it possible to use the Haustein approximation idea to find a local field of characteristic 0 where the character is close?
You mean using the technique, Kashdan technique or the Lean and Kashdan technique of closed local fields?
Yes.
I'm not sure it's possible, because usually it gives you an isomorphism between equal algebras for a fixed level, so maybe it will give you something about character after you average it over a compact open subgroup. But at least for what I know, I don't see how you prove a direct relation between the character functions using this. Except, I mean, outside a certain neighborhood of the singular locus, but of course, the problem happens when you go close to the singular locus, and then you have to change the field of characteristic 0 as you get closer and closer, I guess. I don't know if this answer makes sense, but...
Thanks.
Do you expect to get formulas for the characters as weighted orbital integrals?
Yes, actually it was used in the proof, but I didn't say it. But this is there. On the regular semi-simple locus, not too difficult because you can always basically follow Arthur's proof, which works well as soon as your test function is supported in the regular semi-simple locus. And so indeed you get a formula in terms of the weighted orbital integral, and this was used here. When I say that, because I don't know how to prove this smoothness on the Chandra character without writing it as a weighted orbital integral. And but yes, so we can do it. But I think there is no major difficulty in extending Arthur's proof if you remove everything that wasn't needed, and that uses the characteristic 0 assumption.
Are there any other questions? Not? Let's thank the speaker again.
Thank you.
Yeah. Thank you.
Thanks, Raphael.
Thanks, Dipendra.
Bye.
Bye. How do I escape that? Bye, everyone.